Let's take a look at the ideal gas law. Before we dive into what the equation for the ideal gas law is, we have to go back and recall some of our older gas laws. So if we take a look at Boyle's law, as well as Charles' law, followed by Avogadro's law, we can take all that information and combine it to form the ideal gas law. So if we recall Boyle's law, we talked about how volume was inversely proportional to pressure. In Charles' law, we talked about how volume was proportional to temperature. And in Avogadro's law, we talked about how volume was proportional to the number of moles. Taking all of this together, similarly how we came up with the combined gas law, we can come up with an equation or a proportionality statement, that is to say, volume is proportional to the number of moles times the temperature divided by the pressure. And that proportionality is typically defined by some scale value of some constant. In the past, we've called that constant K. And so we've seen things like K equals V times P, for example, for Boyle's law. In this case, we're going to take it a step further and say that V equals some constant times NT over P. However, when we're dealing with the ideal gas law in particular, we call that constant R. V equals R NT over P, where this R, we call this the ideal gas constant. More commonly, however, we write the ideal gas law a little bit more linearly. So if I multiply both sides by P and I do a little bit of rearranging on the right-hand side, I come up with the equation PV equals nRT, and this is our ideal gas law. Now the question begs, what is this value of R? How exactly can I know what it is? Well, unfortunately, that value of R depends on what the variables are that you are using for that particular question. Let's go ahead and determine R if we're given the units of atmospheres, liters, and Kelvin. So we should recall back to our discussion about molar volume. And the molar volume at STP, which in this case, because we're using liters, Kelvin, and atmospheres, is going to define 1 atmosphere, 273 Kelvin, and if you recall, 1 mole of any gas is going to contain 22.4 liters of that gas. And if I take my gas law equation from below, my ideal gas law equation, and write it in terms of R, I get R equals PV over NT. And by substituting the values above, I see 1 atmosphere, 22.4 liters, 1 mole, and 273 Kelvin. So these are our conditions at STP. You could do this again for SATP or really any combination as long as they work. So this gives us an R value of 0.0821 approximately. And the units here are atmospheres, liters per mole, Kelvin. Now let's change this up a bit, and instead of doing it with atmospheres, let's change it to kilopascals. So it's approximately 101.3 kilopascals. And if I were to solve for R this way, most of my problem stays the same, except instead of 1 atmosphere, I have 101.3 kilopascals times 22.4 liters. Again, that's the molar volume at STP. 1 mole divided by 273 Kelvin. So much more easily, we can simply take our value from before, multiply by 101.3, and you're left with an R value of 8.314, except this time the units are kPa, liters, mole, Kelvin. So all that to say is the value you choose for R is very much dependent on the units you're using. We're typically always going to be using liters and Kelvin, so it really depends on whether or not the problem gives you a pressure value in atmospheres, in which case you would use 0.0821. Some more accurate references will have 8205. Or if it's given to you in kilopascals, you would use 8.314. Both values will give you the right answer if you end up having to convert from one to the other. Of course, if you were given a different pressure like torr or bar or millimeters of mercury, there are R values that exist for those. However, you may find it easier just to convert to our more common units, such as atmospheres or kilopascals.